my great honor to introduce another of my fine scientists, Rebecca Centeno Elliott. I won't attempt to put the correct accents on that.
No pockets. Don't think of it.
Who will be talking to us about Seasick. Seasick is the Community Spectral Polarimetric Analysis Center, which she is the kind of designated lead for, and building capability for future observatories. Okay. Thanks, Rebecca.
Which means I can skip to slide number 2, and now bear with me because you've all heard all of the introduction before. But when we think about the sun's magnetism, we often time picture sunspots, and that's because they're probably the most visible manifestation of magnetic fields on the sun, and indeed they're like host very strong magnetic fields of the order of thousands of Gauss. And they appear and disappear from the sun's surface. They have lifetimes of the order of days and weeks. And in the longer term, though, the number of sunspots on the sun's surface varies with an 11-year periodicity, which is what we call the solar cycle. And although the solar cycle was discovered by counting sunspots, there's a host of other effects and things that vary with this 11-year period. Such as the sun's irradiance, for instance, either spectral or total, the flux of particles, magnetic fields that come from the sun, the number and frequency of explosive events that happen in the sun. This is coronal mass ejections and solar flares. And they're ultimately all related to magnetic fields. However, throughout an entire solar cycle, throughout this entire 11 years, the area on the sun that sunspots and active regions occupy is actually tiny in comparison with the total area. And the rest of the area of the sun is what we call quiet sun, quiet as opposed to active or magnetic. And this is because it was thought a long time ago that the quiet sun was devoid of magnetic activity. This is just a magnetogram of the sun's surface, actually a quarter of the sun's surface. And the black and white patches are just strong concentrations of magnetic field, the two polarities. So these are active regions. Everything outside is what we call quiet sun, and it's gray with a little bit of salt and pepper, like black and white with this magnetic activity. However, when you look really deep and you zoom in to these regions, you see they're actually full of swarming magnetic fields that change, appear and disappear all the time, and they move around. So there's magnetic activity at all spatial scales and at all temporal scales on the sun. The magnetic fields of the quiet sun could be potentially really important because they can harbor, they're estimated to harbor a lot more energy than that of the entire stream of active regions that happen through an entire solar cycle. And this is because there's a lot of them and they're everywhere. Moving on to the big scales again. Another reason why magnetic activity is important is because it's responsible for space weather. Space weather refers to the ever-changing solar-driven events and how they interact with the interplanetary medium. And we hear the term solar storms in the media, which basically encompasses coronal mass ejections and solar flares. And these are very impulsive solar-driven events in which the sun releases large amounts of energy, particles, and radiation at very high speeds into the interplanetary medium. And as you've already heard in many talks before, these can have really potential hazardous implications for us. But again, what I want to stress out is their nature is magnetic in origin. So the sun's magnetism extends out into space, and it reaches very far out into space. This is a beautiful image of a solar eclipse, but it kind of really shows how all of this magnetic structure really reaches out very far into space. And it does so in a spiral manner. And this is because the sun rotates, and as it rotates in its 27-day period or so, it drags the magnetic field out in a spiral pattern. This is what we call the Parka Spiral, and basically any event that takes place on the sun and wants to travel out into space, it will do so following this spiral somewhat and interacting with it. So the magnetic fields of the sun also provide the channels that connect it with outer space, with interplanetary medium, with Earth. So magnetic fields are important, and for a number of reasons. Just capitulating here, they play a huge role in the structure and dynamics and energetics of the sun. They happen at all possible temporal scales, at all possible spatial scales. They're all important in different ways. They connect, or they provide a means of connecting the interior of the sun with its outer atmosphere and all the different layers. They provide means for storing, transporting, and depositing energy among all these different places. They're also responsible for the solar cycle, they're responsible for space weather, and they're important to us. So this is what brings me to my talk. We want to measure them. In order to understand these magnetic fields, we really want to measure them. And the field responsible for, or at least one of the fields, and the most important field, in my opinion, for measuring magnetic fields is something called spectropolarimetry, which I can't pronounce. Spectropolarimetry, sorry, if you've not been here the last few days, that doesn't make any sense, but is the measurement of the distribution of energy and polarization of light as a function of frequency. And it's a really incredibly powerful tool for remote sensing of magnetic fields in the sun's atmosphere. That's why I'm going to talk about it. So spectropolarimetry is 3 words: spectropolarization and metry, which means measurement. Spectrum. So this is a spectrum of the sun. This is what happens to the light of the sun when you disperse it into all of its different colors, frequencies. This is just the visible spectrum, so it goes from very far blue to very far red. It should be linear, but it's cut and stacked up vertically. And you see it scattered with little dark features everywhere. These are spectral lines. You've all heard about them. Spectral lines are places in the spectrum where light of a specific color is missing. And that light is missing because the atoms that compose the sun's atmosphere basically are absorbing little packages of light of very, very specific energies, so of very specific colors. So each atom of each kind at each very specific energy configuration is capable of imprinting a very particular set of lines on the spectrum. And this is the reason why measuring solar and stellar spectra allows us to determine their chemical composition, because each atom has a unique signature on the spectrum. The polarization part of the word. So light is not only characterized by intensity as a function of color, frequency, but also by its state of polarization. And this is because light is a wave. It's a transverse wave. It's an electromagnetic transverse wave, if you want, which means that the quantity that describes light, in this case the electric field, is going to be oscillating in the plane perpendicular to the direction in which it propagates. Right? So you have this electric field quantity that is oscillating in this plane as light propagates in that perpendicular direction. So the way in which this electric field oscillates determines the polarization of the light. So if the electric field is oscillating in a line, we talk about linear polarization. If it's describing a circle in time as it propagates, we talk about circular polarization. And if it just describes a random motion, we talk about non-polarized light. And usually you have a combination of all options, all 3 options. And the reason this is interesting to me is because there are several physical mechanisms capable of introducing polarization in spectral lines. And one of them is magnetic fields. So if there's a magnetic field in the sun's atmosphere, it will imprint polarization signatures in the spectral lines that are formed there. Or in other words, by measuring the polarization of spectral lines that are formed in the solar atmosphere, we are able to determine the magnetic fields that are present there. And that's why spectropolarimetry is a very, very powerful tool to do remote sensing of magnetic fields. Okay, so more quantitatively, sort of, in words, there's 2 sets of equations that describe this problem. One is the radiative transfer equation, which describes how a beam of light that travels through a medium, loses energy as it gets absorbed by the atoms in the medium, or conversely, the atoms in the medium add light to the beam, or it gets redistributed as scattering processes happen. The statistical equilibrium equations, on the other hand, tell us how many atoms of each kind in each possible energy configuration are present in that medium. And as you can imagine, these two sets of equations are really highly coupled in general, because light changes the matter as it travels through it, and matter changes the light. So it's actually a very complicated system of equations to solve. And this is why spectral polarimetry is a difficult science. But let's say we can solve them, and we can. We can in many situations. We know how to solve this problem. What it gives us is, given a set of physical conditions in the sun's atmosphere, if we know the physical conditions of the sun's atmosphere, we are able to calculate the light that would emerge from it. This is the spectral lines and their polarization. So if we solve these equations, we can calculate the light that comes out of the sun. Great. We want to solve the inverse process, of course, because we don't know the sun. So what we want to solve is, given the observations, we go with a telescope and observe our spectral lines and measure our polarization. We want to be able to figure out what the physical conditions in the sun are. So this is what we call, well, that spectral line inversion problem. And I don't really want you to understand this diagram, but there's a lot of arrows, and that's my main point here. It's actually an even more complicated problem to solve, because there's a lot of dependencies, a lot of going back and forth, a lot of iterating going on to just solve the entire thing. But basically what we're trying to do when solving this inversion problem, spectral line inversion problem, is to find an atmospheric model that produces spectra, synthetic spectra, that match our observations really well. So then we can determine that our model is the one that describes the sun's atmosphere. And we still know how to solve this problem in some regimes, in some cases. Going back. Anyway, to another point. Different spectral lines are formed under different physical conditions. So some spectral lines are spectral lines are sensitive to different temperatures, to different pressures, and so on. This means that in different physical regimes, we get different spectral lines, and in different layers of the sun's atmosphere, we get different spectral lines, which we can use conveniently to determine the 3D structure of the atmosphere. So by measuring different spectral lines that form at different heights, for instance, we can extract information from all of them and reconstruct the 3D structure of the sun's atmosphere, if we know how to interpret the spectral lines, of course. And this is what we ultimately want to do is, in my case, determine the 3D structure of the magnetic fields in the sun's atmosphere. Remember the diagram with lots of arrows? Well, we really know how to solve it. We actually really pinned it down for the sun's photosphere. In the photosphere, the physical regime is such that it allows us to make some really simple approximations that kind of decouple all of those equations and allows us to calculate solution very easily. So we know how to go from photospheric observations of spectral lines and polarization to measurements of the magnetic field, and we do so in a very routine and robust manner. Whole different story in the chromosphere, because we can't simplify our equations as easily. All of those simplifying assumptions that we can use in the photosphere, we can't use in the chromosphere anymore. And that means we have to solve that whole complicated diagram. And it's a very hard problem. And people do solve it nowadays, but with buts, with caveats. Now, I was supposed to talk about Seasick. Seasick is the Community Spectral Polarimetric Analysis Center, sorry. And it was born, well, it was an 8-year strategic initiative. I should have asked Bruce before this talk when Seasick started. I believe it was around 2003, but I'm not really sure. I failed to find him before the break. But it was born from HAO's heritage and expertise in the development of spectral polarimeters and the interpretation of polarized light for remote sensing of magnetic fields in the sun's atmosphere. And the most important word there for me is community, because Seasick was envisioned as a community resource built in collaboration with the community, so getting all of the wisdom out there in the community in order to support the community. And Seasick was born at a time when we were preparing for the launch of the Hinode mission. Hinode is a Japanese, UK-US mission satellite that was going to carry on board this spectral polarimeter that was conceived at HAO and developed in collaboration with Lockheed. And the spectral polarimeter was going to measure the polarization in 2 photospheric spectral lines of iron. And in this context, Seasick, which at the time was led by Bruce Lights, developed the data pipeline for this instrument and not only provided calibrated spectra for the community, but for the first time in a routine and automated manner, it actually provided the results of spectral line inversions of this data. And this is higher level data products such as the magnetic field vector, the plasma velocity, and so on and so forth. And this was really a breakthrough in some ways because it allowed that portion of the community that has no expertise in polarization to actually use this very unique data set. And I think it was a huge benefit for the solar community. Nowadays, Seasick, I mean, we still do that. We maintain the Hinode data stream. We provide software tools, documentation, user support. Oh, this is just an example of data levels, how Seasick goes from this spectra to things like this, which is magnetic field inclination, magnetic field strength. This is what the community needs when they don't know how to interpret this. The other part of the title of my talk that I was given, by the way, is building capability. Look at you, but. So Seasick will be supporting upcoming new instruments. In the short term, CHROMAG, Chromospheric Magnetometer, whom Sarah briefly introduced in her talk. I'm not really going to talk about it. And the whole suite of instruments on DKIST, who Valentin talked about yesterday. As far as I know, of all of the first light instruments, I think only one does not have polarimetric capabilities. And Seasick wants to be there to help with the interpretation of the data that come from all of these instruments. And you know, as every time you put a new instrument out there with new capabilities, enhanced capabilities, you get to see aspects of the sun that you've not seen before, whether it's new spectral domains, whether it's in better spatial, spectral, temporal resolution, whatever it is, you get to see things that you've never seen before, and you'd better be prepared to interpret them. So this is another place where Seasick comes in, and it's very, very ambitious. But we really want to, as part of the community, get our acts together to really provide those tools for the interpretation of these new data, especially for the chromospheric radiation that we still not quite have pinned down how to do. The other part of building capabilities is the community involvement aspect of Seasick. Seasick really takes from the community all of its wisdom and brings it together, but we also need to, this involvement goes both ways. We need to give back to the community in the form of service in data, service in giving tool, analysis and software tools out, but also education and collaboration. And this is my last slide on the education aspect. For the first time, Seasick is getting involved in the development of a curriculum for a spring course at CU called Topics in Solar Observation Techniques, and in particular, in this part of it called Spectral Polarimetric Diagnostic Techniques very appropriately, because we do believe that we really need to educate the next generation of solar physicists in the area of spectral polarimetry if we want to keep this field alive and if we want to keep unveiling the secrets of the sun's magnetism. So I'm just going to leave it at that. Thank you, everybody. This is our website. We really appreciate comments, help in building this tool. We need community involvement. Thanks.
Thank you, Rebecca. Yeah, it's pretty challenging to go all the way from the photosphere through the chromosphere to the corona, and so, you know, we want to build that capability to help understand, you know, both the structure of the magnetism and then ultimately help with the flow of energy. Do you have any quick questions? Michael?
I want to give you the background on how this came about.
Yeah.
It was, I think, in 1996 that Bruce Lights, B.C. Lowe, and I went to NSF and suggested something that we called a solar magnetism initiative, because we saw the potential to develop magnetic field measurements of all layers of the solar atmosphere, and in view of the new instruments that were kind of dreamed up at the time. And as usual, it took a long time to make any hay out of this, though the community response was very strong. And the only piece of sort of additional funding that came out of this was Seasick, which, in view of that, DKIST is now one of the largest investments that NSF has done in a facility, $340 million. It is, I think, for us as the accompanying think tank for the community, for us to develop all these tools is I think, essential to help NSO to bring out the best.
I agree, and I'm sure Valentin does too. Okay, thanks again, Rebecca.